is Dr. Nader Al-Bastaki from the University of Bahrain. Now we're talking about modeling using Comsol of absorption into a falling film in laminar flow using Comsol. Students have already covered this topic in the classroom and have solved problems by hand, and we want to see how to do the same, solve the same problem using Comsol. When we start Comsol version 5, we come to this screen, so we select Model Wizard, and then we select 2D. Now in our problem we have two types of transport processes. First one is the mass transfer. So let's select the chemical species, and then transport of diluted species. And the second set of equations we need are the equations of momentum transfer. So let's select fluid flow and single phase flow and laminar flow. So we have, as you can see, the selections down here are laminar flow and transport of diluted species. Next, select study, and we're going to select stationary for steady state operation. We have the steady state or stationary selected, as you can see here. Select done, and we can start the modeling. As you can see here, this is the first page of the Comsol model. Let's start with defining the geometry. Let's go to geometry, right click on geometry, select rectangle, and the dimensions, let's make the thickness of our problem is a thin film falling down a vertical wall, and we'll select the width or the thickness of that film to be 2 millimeters, so 0.002, and the height we'll keep it at 1 meters. And next we have to click on build all objects so that that geometry is created, as you can see here. The next step to do is to select the material. So let's go to materials, right click on materials and select add material, and you can go to the right hand side here and search for water. Our solvent is going to be water, and we're going to have a gas that is being absorbed into water. So search for water and then select liquids and gases and liquids, and go to water here and right click, then add to component 1. As you can see here, water has been added to component 1 under the materials icon. The next thing to do is to define our boundary conditions and properties for the mass transfer. If we select transport of diluted species, you can see that our geometry here has been labeled as number 1. If you click on 1, you can see that has been highlighted, the color has changed. And these are the equations of Fick's first and second law that will be used in this problem. So let's go to transport properties and define our diffusion coefficient. So click on 1 here just to highlight our geometry and go down to the diffusion coefficient. Let's give it a value. The default is 1. e minus 9, make it 1 e minus 7. And next go to the no flux. Actually, by default, all of the 4 volts are assumed to be initially with no flux, but we're going to change that. Before we do that change, let's go to the initial values. Click on 1 here, which is the whole rectangle, and the default concentration, initial concentration throughout the liquid in that stream or in that rectangle geometry has a concentration of 0. We don't want to keep that, so let's keep it at 0 moles per cubic meters. Having defined the boundary, the initial values, let's go to the boundary conditions. So go to transport of diluted species, right click and use a set of possible boundary conditions. We will define the inflow, the outflow, and we'll define the interface. First, let's go to the inflow. The inlet to this liquid thin film will be at the top. So let's zoom in by drawing a zoom box at the top end here, and perhaps you can do that a second time to make it larger. We're going to select this hole as the inlet, and you can see it has been highlighted or given the label 1. Let's highlight it by clicking on it. Now the concentration, default concentration is 0. We can change it. If the solvent is being recycled, typically in the industry, it will have traces of your solute. Let's assume that this is fresh water, so the concentration of the solute will be 0 in the incoming liquid. The next boundary to define will be the interface, which is on the right hand side. The left hand side will be just solid wall, no flux through it. The right hand side, this is where the interface exists between the gas on the right and the liquid on the left. On the left, the gas dissolves into the liquid through this interface, and the concentration of the solute or the gas on the interface, on the liquid side of the interface, will depend on the solubility. So let's so the concentration will be actually the solubility of the gas in the liquid. So let's go back to transport of diluted species, right click and select concentration, then select this one and click on number 4, which is the label flat wall. You can see the color has changed. We're going to give that interface, the liquid side, on the liquid side, a value which is equal to the solubility of that solute in the liquid, and let's assume that value is 5e minus 3 moles per cubic meters. The final boundary to specify is the outlet, so go to the transport of dilute species, right click and select the outflow. It is hidden way down, so let's zoom out by clicking this and then zoom in again on the lower end. Draw a box here. That's a second time. Now highlight the outlet for that wall. Define it as an outlet. So that's wall number 2, and this is your outlet. The final wall, which is the left hand side, is already by default is no flux. If you go to no flux, all of the three other walls now have been defined, they're overridden. The only one, which is a no flux wall, is wall number one. This is this left hand side wall. So we're through the boundary conditions and the initial condition of the mass transport side of the problem. Let's go to the flow side, or the laminar flow. Again, here we have to define the properties. First of all, if you click on this, you can see that the domain is labeled as number one. If you click on it, the color changes here to green. These are the transport, momentum transport equations that will be used. And let's go first to the properties by clicking the fluid properties. Go down the menu here, you'll find the temperature is by default at 20 degrees C. Let's keep it. The density and the viscosity are taken from, by default, from the material, which means in this case the water that has been already selected. You have the choice of defining your own material if you wish. Let's keep the properties, water properties from the library. Next, let's go to the initial values. Again, click on one, and you can see that the three components of the velocity x, y, and z have zero values, and the pressure, the gauge pressure by default is zero. Let's keep all of these, no need to change these at the moment. Finally, let's go to the boundary conditions. Click on laminar flow and right click to define the boundary conditions. Again, you have to define the inlet, the outlet, and the interface. Let's start with the outlet, since we're zoomed in on the lower part of the diagram. So select the lower wall as your outlet, and here we can actually specify the pressure, but in our case let's keep the gauge pressure to be zero, which means 1 atmospheric pressure. Next, we can define the interface. Now, the left wall is already by default a solid wall with no slip condition. All walls initially are defined by default as no slip condition. Right now we've redefined the outlet. Let's redefine the right wall, which is the interface between the gas on the right and the liquid on the flowing liquid on the left. And to define it as an interface, we know that the velocity on the wall here is zero, and the maximum velocity is at the interface. And for a fully developed flow, the flow will be half a parabola, and the velocity profile will not change with time or with distance along the y-axis. To do that, or to tell Comsol that condition, we're going to select as the opposite of no slip, which is a slip condition. So let's go to laminar flow, right click, and select wall. Click on the right wall here, and let's go to the boundary conditions here and change the no slip condition to slip condition. And finally, the inlet has to be defined. So let's go to laminar flow, right click, inlet. We have to zoom out first and then zoom into the upper part of the diagram. And let's highlight or click the upper wall. So wall number 3, which is the inlet, or upper wall, is going to be our inlet. Here actually you can again give it an inlet value. Let's assume it's 0.1 meters per second. The final wall that remains actually is the left wall. By default it's already an offset wall. And if you click on this, you can see that all of the walls have been, all of the 3 other walls have been defined by us except for wall number 1. So wall number 1 by default is a no slip wall. So we don't need to change that. We finished now defining the boundary and initial conditions for the mass transport and the momentum transport parts of the problem. Now finally we need to carry out an action that is necessary. In this case, in the classroom we did that by drawing an element, a volume element. We need actually to couple or link the mass transport and the momentum transport equations. Right now, so far, Comsol will view each sets of those 2 equations as separate entities. So we need to ask Comsol to link them or to couple them. In the classroom, what we did was to draw a volume element, rectangular volume element in the film, and we looked at the flow coming with the velocity vertically, coming into the film and then exiting the film, and we multiply the flow rate by the concentration at the inlet and the concentration at the outlet. Horizontally, we had the diffusion taking place, the diffusion brought in to the volume on the right wall here, a certain amount of solute, and on the wall on the left, a certain amount was leaving of the solid A was leaving by diffusion. By doing a material balance on using those equations, we arrived at a coupled equation which combined the effects of velocity on the concentration. To do that on Comsol, you go to multiphysics, right click on that and select flow coupling. And as you can see here, the laminar flow as a source, destination, transport of the polluted species. Final thing to do is to go to the mesh and generate the mesh. By default, it's on normal. Let's select a coarse mesh just to reduce the amount of processing. And then select build all to generate the mesh. It will take a few seconds, as you can see. Now the mesh has been generated. The mesh consists of triangular finite element shapes with a random size, randomly generated by Comsol. The intensity of the of the mesh is higher near the wall. Finally, we're ready now to start the calculation, so let's go to step 1 and select compute. The calculations have started, as we can see down here. And if you need to follow what's happening regarding the convergence, you can actually go and click on this tab here. We can see that in a short period of time, the error size has already gone beyond 0.01 or 10 power minus 2. Finished. We can see nice concentration distribution as expected near the interface on the right hand side. The concentration is the maximum, which is the value assigned by us as a boundary on the right of the interface, while on the left hand side it is 0. This is at the upper end of the geometry. If you zoom into the middle, say, you can see a different picture. You can see that the solid has diffused towards the end of towards the side of the film, falling film. What we can do in addition to this surface diagram, of course, you can look at the velocity profile as well as the pressure profile. Click on the velocity. This is the velocity profile. As expected, on the left hand side, the velocity is 0. We have a no slip condition. The maximum is on the right hand side. If you click on the diagram at any position, you can read the values of the velocity down here, or the concentration if you're plotting the concentration. At any position, you can see that the actual values of the velocities are being displayed here. Finally, let's try another type of a plot, which is a line plot, by drawing the concentration profile, let's say, in the middle of the height of the film. So let's say at the height of 0.5 meters. And let's see how the concentration profile varies from the left wall to the interface, from the wall to the interface, from left to right. And we can, in a similar way, we can plot the variation of the velocity. And we can also plot the variation, say, of the concentration from top to bottom along the center line. So let's start with the height of 0.5. And to do that, we'll start with data sets here. Right click on data sets and select cut line 2D, and then we have to give it dimensions by giving it the x and y coordinates of 2 points. So the first point will be on the left hand side here, so it will be an x of 0 and a height of 0.5. And the second point will be same height, which is 0.5, but the x will be the thickness of the thickness of the wall, which is 0.02. Okay. And to check what you've done, just click on plot, and you can see that a line has been drawn here. If you zoom in, you can see that X and Y uh, uh, arrows have been drawn to show the direction, the positive directions. Right, next thing to do is go to the results and right click on the results and select a 1D plot group. You can see that we have a new tab here generated called 1D plot group 4. You can change the label here if you want. You can call it concentration. At 0.5 meters height, for example. And let's go to the data set and select the cut line to D. This is where we want to pick our data from, to plot here. You can give the X and Y axis labels. Say X will be horizontal distance, at 0.5 meter height, and that distance will be in meters, and the Y will be the concentration in moles per cubic meters. If you click plot, you can see that labels have already appeared here. Next thing to do is to go back to this tab here, concentration, which we've given now a new label. Right click on that and select line graph, and default expression here to be plotted is the concentration. So we want to plot the concentration, so we'll keep that. But the only thing you need to change here is where you're going to pick your data from. So click on this data set here, click on the arrow on the right, and then select cut line to D1. And we're ready now, so click on plot, and that gives you the concentration profile across the thickness from 0 to 0.002 at a height of 0.5 meters. Now let's repeat the same thing for the velocity. So to do that, let's go to results, right click on results, and select 1D plot group. So now that gives you another tab. Again, we can change the tab here. We can call it velocity at 0.5 meter height. And we need to select the source of data. Again, it's going to be cut line to D1. The X label, again, is going to be distance, or let's call it horizontal distance. Horizontal distance at 0.5 meters, units of meters. And the y-axis is going to be velocity, meters per second. And if you plot this, now all the labels have been changed here. Actually, I haven't, you can select a title also for the graph if you wish. I haven't done that, I'll leave that for you to do. Now let's go to this tab here, velocity at 0.5 meters height. Right click on that and select a line graph. And now we have two things to change. First, the source of data has to be from the Catline 2D, so go to that and change it. And the expression, the default is concentration, we need to change that. So click on this arrow here and select laminar flow, and we want to plot the velocity magnitude, which is over here. Okay. And the units, you can change it or you can keep it. Let's keep the units. So already now we've selected the expression and the source of data. Let's select plot, click on plot. So that gives you the, as expected, the velocity is 0 on the wall and maximum at the interface. And it's a parabolic shape. Finally, we can plot the, as I said, the concentration distribution from top to bottom along the center line. So to do that, we need to go back to data sets. The cut line 2D one was at a height of 0.5 meters across a thickness. Now we have to define a new cut line 2D. So go to data sets and select, right click on that and select cut line 2D. So that gives you a cut line 2D 2. Now we have to give it the dimensions. The dimensions is going to be on the center line, so vertically though, so the x is going to be 0.001 and y, we start at y0, and the second point is going to be x again 0.001, and the height, the y value will be 1. To make sure we've done the right thing, just click on plot, and you can see, of course this is zoomed in, so if you zoom out and then I can zoom in from the top side, it will be more evident. You can see the shape of our lines going through the center from top to bottom. So we want to plot the concentration profile along that line as the liquid enters from the top with a 0 concentration, and it absorbs the gas from the interface on the right. So it's going to be absorbing until it reaches the end with a maximum. So it's going to exit the maximum concentration. So to do that, to ask it to plot that concentration, we have to go to results now. Right click on results and click on 1D plot. So now we have a new plot group here called 6, group 6. We can change its title, we can call it, let's call it vertical concentration. And actually we can define the data set as we did before. It has the output line 2D2 and the labels again. Now is the vertical distance along the center line. Meters, and the y-axis is going to be concentration. And then in moles per meter cubes. And if you plot that, you can see that the labels have been printed here. Now, The label has also been changed here. Let's right click on that now and select a line graph. The default is concentration, so we don't need to change that, but we need to change the source of data. So click on the arrow here, and now we need to select the right source, which is cut line 2D2. If you select 2D1, that will take you to the previous situation, and it's going to be screwed up because now we define the axis in a different way. So select cut line 2D2, and I guess we're ready now. You can click plot, and that gives you your concentration distribution from top to bottom. So at the top, the y value of 0, sorry, the bottom has a y value of 0, the concentration is maximum, and the top with a y value of 1, that is the inlet, the concentration is 0 as expected. So this agrees with what we expect from the problem. So now we know how to plot line diagrams at specific positions. You can select any position along the geometry that we have to have an idea about the profiles of concentration, velocities. Of course, we've got many other parameters that you can plot. I hope this was a useful introduction, and I expect all the students in the class to be ready now to do the assignment using Comsol. Thank you very much, and see you another time.